We've talked briefly about the methods of um, heat transfer, of heating, but we didn't talk about the mathematics of it. So now let's talk about the mathematics. Usually what we're interested in is essentially a power. We want to know the power or the rate at which thermal energy, heat, is transferred with respect to time. Now, if I've got a hot place and a cold place, what might affect how quickly heat flows from one to the other? Let's suppose this is a house, and it's nice and warm and toasty inside, and it's freezing cold outside. Well, we would think the bigger the temperature difference, the faster energy would move from the inside to the outside. So we would expect this to have a term that's equal to the difference in temperature, hot temperature minus cold temperature. Notice this is a temperature difference, which means we can get away with using Celsius degrees or kelvins. It's not going to matter because it's a temperature difference, not an absolute temperature. Next, we would think that the bigger this area, the more energy would be able to flow through it. So we would expect this to be proportional to area. We would think that the thicker the wall, the less rapidly energy would be able to flow through. So we would expect to have that length here in the bottom, and then we would expect to have something dependent on the kind of material. A metal wall would let energy through much faster, a wood wall would let it through much slower. So that is called the conductivity. And so we find that the power goes through at a rate equal to the conductivity times the area over the length times the temperature difference. This is not that different from resistance. Remember, for resistance, we had that it was equal to the resistivity times the length over the area. Well, if we replace resistivity by 1 over resistivity, which is conductivity, we have L over conductivity times A, which is exactly the inverse of this part right here. So this is our formula for the rate at which power flows through conduction, through a wall or any other object. It's fairly straightforward to work with. I'm not going to do too much in the way of examples. Here we have a series of thermal conductivities for various different materials. Metals tend to be pretty low. No, moderately high. I'm sorry. Steel, not great. Lead, not great. But aluminum, copper, silver, they conduct really well. In fact, that's why you tend to have at least the bottom of pans be made out of aluminum or copper, because by having that high conductivity, you get a nice even temperature across the bottom. If it's a stainless steel pan, this conductivity is not high enough, and you don't want to use that if you're looking for a nice even temperature. You can make the sides of the pan out of it, but you want something covering the bottom made out of aluminum or copper. Next thing you might notice is that air has a really low conductivity. Air is a really good insulator when it comes to conduction, which might make you ask the question, why, if I have a house made of standard walls, which have big air gaps in between them, why isn't that house nice and warm and well insulated? Why do I have to start adding things made out of glass to make it better insulated? You'll notice fiberglass here actually has a coefficient slightly worse than air's, and the reason for that is that the glass itself is not a terribly good insulator. The coefficient of the conductivity of glass is quite a bit higher than air's. The key point is that air convects. So warm air, air near the inside of the house tends to get warmer and warmer and warmer and rise. Then it moves over to the outside where it gets cooler and cooler and cooler and falls down. And even though air is a lousy conductor, these cycles will transport a lot of energy from inside to outside the house when it's on a cold day, and it'll transport it the other way on a warm day. What things like polyurethane foam, rock wool, fiberglass do, they are mostly air, and most of the insulation is done by air. But what they do is they set up a bunch of little pockets of air, so that rather than having a great big convection cycle, at most we get little tiny convection cycles which are not very efficient. As a result, air is no longer able to transport energy by convection, it can only transport it by conduction, and as you can see, air is a lousy conductor.